Good morning, everyone, and welcome to today's webinar on Generative AI for Tax, Handling Challenges of LLM Deployment and Integrating Reliable Components. My name is Zhengxiao Ying, and I'll be your host today. Thank you all for taking the time to join us. So before we dive into the details, let me give you an overview of what we'll be covering today. To begin with, in Meet Your Speaker, I'll share a bit about my background and what our company, Algonomia, does. Following that, we'll take a look at the concept of artificial intelligence, AI, and large language models, LLM, to understand what they are and how they work. Next, we'll explore the various applications of LLMs, as well as discuss their limitations. Then, I'll introduce you to how we've integrated LLM solutions into Algonomia's Live platform to facilitate tax processes. Afterwards, we'll explore the development approach we've adopted for these LLM components, highlighting best practices and challenges we've overcome. We'll also show you how our solutions work through a live demo and discuss the next steps for LLM-related development on our platform. And of course, we'll leave some time at the end for any questions you might have. Our goal today is to provide you with a deeper understanding of large language models and how they can be effectively integrated into tax processes to enhance efficiency and accuracy through a demonstration of how we are integrating certain LLM components on our platform, Live platform at Algonomia. Hopefully, by the end of this webinar, you'll have a clear picture of both the potential and practicalities of deploying LLMs within your own tax functions. So let's get started. Once again, my name is Zhengxiao Ying, and I am a data scientist at Algonomia. I specialize in deploying AI technologies to make tax processes more efficient and easier to manage, as I have a dual experience in both transfer pricing and data science. I've worked as a transfer pricing consultant at EY in Tokyo and as a data consultant at Orange in Paris. I also hold a master's degree in data science and business analytics from ESSEC and Centrale-Supélec. Now, let me quickly introduce the company behind today's webinar, Algonomia, a French startup founded in 2017. Our mission is simple yet ambitious: to give back control to tax departments through digitalization by leveraging SaaS solutions. What makes us different is our diverse team, bringing together experts in tax, mathematics, engineering, data science, and design. This mix of skills helps us create innovative, reliable, and user-friendly solutions that truly meet the needs of tax professionals. We've also had the privilege of working with several large multinational companies, including Renault Group, Schneider Electric, Alstom, ENGIE, Epson, and many more. Additionally, we've partnered with leading firms like Deloitte and Fidal and have established academic partnership with EDEC and EDEC. They are a top French law school and a French business school. So, at the heart of our offerings is the Live platform, which is designed to simplify the complex landscape of multinational tax compliance. Each Live on the platform represents a specialized tax application that caters to specific client needs. For example, our PI2 Live helps manage Pillar 2 requirements, while the ATP Live simplifies transfer pricing computations. So, now that you've gotten to know us a little better, let's move into the main part of today's webinar. We'll begin with a brief introduction of AI and LLMs. As many of you know, AI has become more than just a buzzword in recent years, and that's largely due to its dramatic improvements, especially since around 2017. Over the past few decades, AI systems have steadily improved, but it wasn't until recently that they truly began to rival and even surpass human performance in language-related areas, shown on the right part of this graph. So here in this graph, it shows how AI systems have progressed across different capabilities, with human performance used as a baseline, shown in green, this line. As you can see, AI has reached a good level in handwriting, speech, and image recognition over a decade ago, but its improvement in language-related areas, including reading comprehension, language understanding, and predictive reasoning, didn't begin until 2017. So one of the key drivers of this surge in AI performance has been the rise of large language models, or LLMs. LLMs have played a pivotal role in these advancements, thanks to the transformer architecture which was introduced in 2017 by scientists in Google. This new architecture enabled AI models to handle and understand language in ways that were previously impossible, unlocking powerful new abilities in areas like language understanding and reasoning. Now you may be wondering what a transformer is. Don't worry, I will explain about it and how the transformer architecture made all this possible later in this section. But first, let's take a look at what exactly AI and LLM are and how they work in this slide. I will break down the connection between artificial intelligence, machine learning, deep learning, as well as generative AI, in order to understand where large language models fit into the picture. So, artificial intelligence refers to technology that enables computers to perform tasks that usually require human intelligence, like recognizing patterns, making decisions, and solving complex problems. Next, many AI systems are powered by machine learning, a core area of AI where computers learn patterns from data and use that knowledge to improve their performance over time without needing explicit programming for each task. And there is a more advanced type of machine learning called deep learning, which uses layers of neural networks similar to how the human brain works to process data, helping machines learn even more complex patterns, such as those in images and text. And one type of deep learning model, known as generative model, can generate new data with similar characteristics to the given data. Generative AI, or Gen AI, is built upon such models. Instead of just analyzing or recognizing data, Gen AI creates new content like human would do, such as text, images, or videos. Finally, we arrive at LLMs. These are advanced language models that can understand and generate human-like text. They are called large because they are built on massive amounts of data and usually have billions or even trillions of parameters to train. Technically, LLM is not just a subset of Gen AI, as they can also perform non-generative tasks in natural language processing. However, in the current AI boom, we are primarily focusing on the ability to generate text content or even images with multimodal language models. So in this context, Gen AI and LLM are often used interchangeably. Next, let's dive a little deeper into why deep learning became necessary, especially when dealing with unstructured data, that is to say, data like images, videos, or text. Traditional machine learning methods work well for structured data, such as tables and numbers, because they can easily identify patterns and relationships in well-organized data, where each feature is predefined and labeled. For example, in a dataset of customer purchases, machine learning can analyze the quantities and categories to predict future buying behavior based on patterns it finds. However, when it comes to understand unstructured data like text or images, it's almost impossible to predefine and label every feature. Traditional machine learning then struggles. For example, if you want to use traditional machine learning to identify whether an object in this picture is a car, it would require a lot of manual feature engineering. This means we'd need to tell the machine exactly what to look for, such as wheels, windows, or specific shapes, and also explain how to detect these features in various situations, like when the car is facing forward or when it's seen from the side. Obviously, it's very time-consuming and requires a lot of effort. This is where deep learning steps in. Deep learning allows the machine to automatically learn the features of the data on its own without needing specific instructions from us. It uses layers of neural networks to process and analyze the data, enabling the machine to discover the important features by itself. So as long as we feed the machine enough images and tell it which ones contain a car, the machines will learn to identify the defining features of cars in various scenarios. Eventually, it will be able to correctly identify a car in an image, even though it hasn't seen before. So we can totally skip the manual feature extraction step. This capability has made deep learning incredibly effective for tasks like image recognition, speech processing, and of course, language understanding with the advent of the transformer architecture that we mentioned at the beginning. So transformer is a specific deep learning architecture. It is one of the most important breakthroughs that made language models possible. Two key innovations in transformers have revolutionized how machines understand and process text. First, it uses contextual word embeddings. Word embeddings is a technique that converts words into a bunch of numbers as machines only take numbers, not words, as input. Imagine that every word in a sentence is given an ID card, a unique set of numbers that helps the machine recognize and process the word. Traditional language models use word embeddings where each word had a single ID, even if the word had multiple meanings. For example, the word apple could refer to the fruit or the company. But the machine wouldn't know which meaning to use. Transformers, however, create contextual embeddings, meaning the model adjusts the embeddings of apple based on the words around it. We can see it as different ID cards can be assigned to the same word based on its context under the transformer architecture. So for this, when it means fruit, it gives in the word this ID. When it means company, it will give the word this ID, for example. This was made possible by the second key innovation, self-attention mechanism. It allows the machine to weigh the importance of each word in relation to the others in a sentence, regardless of their position. For example, in the sentence, there are two apples in the basket. The machine can understand that apple refers to the fruit mainly because of the word basket. And in another sentence, Apple's stock price is on the rise. It would know that Apple refers to the company because of stock price and thus assign appropriate ID cards accordingly thanks to this self-attention mechanism. This capability has revolutionized AI models' ability to handle text, making them much more accurate and versatile. Now that we've covered the basics of LLMs, let's explore what they can actually do. So, through a prompt, which is simply an instruction or question we give to the LLM, LLMs can perform various language-based tasks, including generation, summarization, translation, classification, and chatbots. Here is an example of a few of these tasks in action. For example, for translation, when prompted to translate English to French, that is good, the machine returns c'est bon. It can also be used as a chatbot to give you recommendations for Italian restaurants in Paris. These examples show how LLMs can take inputs and generate meaningful, context-aware outputs across various tasks. Despite these impressive capabilities, LLMs are not perfect. One of their biggest issues is something called hallucinations. These occur when the model generates information that is false, nonsensical, or not supported by the given prompt or data. Sometimes, even if the prompt is clear, the model can still generate incorrect or misleading information. For example, here is an actual conversation I had with ChatGPT-4. When I asked it, who is the first person to cross the English Channel completely by foot, which is by no means possible to accomplish. ChatGPT responded with this text. He gave me a name, Matthew Webb, who was a British swimmer and was the first recorded person to swim the English Channel in 1875. I fact-checked this part. It's not relevant to my question, but it is true. The problem lies in the latter half of the response. The model hallucinated the part about Matthew Webb walking across the channel, which never happened and is not possible to ever happen. This is a clear example of LLM hallucination. Another limitation of LLM is their limited context length, which is defined as the number of tokens they can process and take into consideration when generating text. To understand this, let me first clarify what a token is, so you can take a look at the bottom right part of the slide. So a token is a small unit of text, which could be a word, part of a word, or even just a character. For humans, the smallest meaningful unit in language is often a word, but for LLMs, it's a token. Tokens can be based on whole words or subwords. For example, in this case, while in subword level, while many tokens correspond to full words, more complex words, such as those with conjugations, may be split into root parts and grammatical elements, like the word tokenizing here. So the token is split, the tokenizing is split, and the token is the root part, and the izing is the grammatical element. So most LLMs have a limit on the maximum number of this kind of tokens they can handle, as shown in this table. For example, if you are sending some documents to summarize to an open source Llama 2 model developed by Meta, this green logo means open source, and open source means that the source code of the model is publicly accessible, allowing anyone to view, modify, and distribute it freely. So this Llama 2 model has a maximum token limit of 4,000, and if you give the model a document to summarize that takes up to 3,700 tokens, including its response, you're already close to that limit. If you then ask the model to compare this document with another one that you sent to the model before, using another 300 tokens in the prompt, it will reach the 4,000 token limit. These 4,000 tokens of prompts and the responses make up this rectangle, which is called a context window. The model can only access information inside this window when generating new text. As the old document was sent before the rectangle, the model can't access the content because it has already reached its token limit. In simpler terms, the model can't remember the first documents because it's out of space. In this case, the model will fail to give you a proper response. And as a side note, if the number of tokens in a single prompt exceeds LLM's context length, you will simply get an error. Moreover, LLM also face limitations when it comes to security, privacy, and complexity, especially in corporate environments. Let's break this down into two common scenarios of deploying LLMs. The first scenario is using third-party LLM APIs to access commercial LLMs like ChatGPT. But when using services like ChatGPT or Gemini via API calls, there are significant concerns about data leakage and confidentiality. Sensitive corporate data sent to third-party providers can be at risk of being used for training or policy review, which can compromise privacy. Additionally, the cost can skyrocket when you need to process many large documents. For instance, generating a summary for a local file with 150,000 tokens using OpenAI's GPT-4 32K model can cost nearly 10 euros for a single document. The second scenario is deploying open source LLMs on-premise, which means in your own company's own servers. So running LLMs on your own servers while being much safer requires resource-intensive infrastructure. Renting high-performance GPUs, such as NVIDIA's 800 V4 series on Microsoft Azure, would cost over 20,000 euros a month. You also need skilled personnel to manage and integrate these models, and they are often highly specialized and expensive to hire. Lastly, model limitations come into play. Often on-premise solutions are restricted to open source or sub-tier models that may require complex prompt engineering to achieve the desired performance. So these limits are all factors to be taken into consideration when using LLMs for business purposes. Given the capabilities and limitations of LLMs, It's crucial to consider several factors before deciding on the deployment method. Some key questions include, is their confidential data involved? If so, you might need to consider on-premise deployment or strong privacy measures. Can you provide multiple examples for your tasks? If you can, include these examples in your prompt can help the model produce better results. Do you have tools to inject knowledge into the model? If you need to integrate specific domain expertise in a cost-effective way, tools like retrieval augmented generation, RAG, which we'll talk about later too, would be very helpful. Do you have a large amount of domain-specific data for fine-tuning? If so, fine-tuning can significantly improve the model's performance in specialized areas. However, it's more resource-intensive than using RAG, as it requires more data and more GPU resources. Lastly, do you need to build your own LLMs from scratch? This would require millions of dollars and billions of tokens for pre-training, and it's a huge undertaking, usually only feasible for very large tech companies. For most of us, this is not a realistic option and will not be considered. So, as you can see, the complexity and cost increase as you move from simpler tasks to more customized pre-training solutions. In short, the more complex your need is, the more resources, data, and infrastructure you require. And at Algonomia, we've carefully considered these factors and have already taken the first 3 levels into account in our deployment strategy. On our Live platform, we've implemented summarization and keyword extraction, which is a key step in tag generation to make managing financial documents more efficient. We are also exploring the 4th level, fine-tuning LLMs with domain-specific data to create customized solutions tailored to our clients' needs. In fact, we've already used fine-tuning to adjust performance of smaller models by leveraging the responses from larger models, which will help us use few resources while still achieve high-quality results in the production environment. All of these strategies allow us to continuously adapt and enhance our LLM-powered features, ensuring they meet the specific demand of each client. Now, let's explore some of the ways generative AI or LLM can be applied on text functions. First comes summarization. LLMs can summarize content from any attached document or file, whether it's a questionnaire, a risk assessment, or even a data table. This can save time for tax teams by offering concise overviews of complex documents. Next, translation. LLM can handle not just document translation, but also translating any data collector forms, tables, questionnaires, or even the entire user interface of the platform. This can be particularly useful for multinational teams working in different languages. And text generation. In the context of transfer pricing, TP documentation writing, for example, LLMs can assist in drafting parts of reports like introductory sections or data explanations, reducing manual effort. And classification as well. LLM can classify documents and files, allowing for automatic tag generation. This makes organizing and retrieving financial documents easier and more efficient. Last, data extraction. LLMs can extract relevant data from any document or file, whether it's a risk analysis, a questionnaire, or other tax-related materials. They can even assist in document interactions, like identifying key information with complex reports. Currently at Algonomia, we are implementing summarization and classification through tag generation on our platform, and we'll take a look at them later. So now, first, let's look at how we've integrated these LLM components into the Live platform. So the implementation architecture follows a specific workflow. First, client upload files onto the platform. Then, optical character recognition, or OCR, is used to convert these documents into machine-readable text. Next, we prepare the appropriate prompts for the LLM to process the content. The model then processes the text and generates output based on the prompt. Finally, the processed data is made available on the platform for further use. One important feature of our architecture is that LLM processing is done on dedicated VM resources that are separate from the main platform's resources. This separation is crucial because LLMs, while powerful, are not 100% reliable yet. There can be occasional errors, or clients may want to adjust the output format. By separating LLM resources, we can debug or adjust these outputs without disrupting the rest of the platform's core functionalities. Moreover, data flow is fully protected throughout each stage. All VM resources are dedicated to individual clients, ensuring there is no risk of data exposure or cross-client contamination. This is essential for handling sensitive corporate data securely. Now, let's look more closely at how we process documents on the platform. When a document is uploaded, it is first saved in the document database. The document undergoes OCR processing to convert the content into text, which is then stored in the database. This text can be used for simple text research within the platform. The text is then passed through the system for tag generation and summarization. For now, it supports from any language to English and French. These data points are batch processed by the LLM and stored in the database, allowing users to access them at any time. We use batch processing to reduce costs, so GPU resources are only needed during specific times of the day. By turning off these resources when not in use, we can manage the infrastructure costs much more effectively. In the future, we plan to introduce real-time LLM processing for more dynamic features, such as on-the-fly summarization into different target languages other than English and French, and data extraction for direct document interactions. However, these real-time features may incur additional costs, which we are actively working to minimize, and they will be implemented based on client demand. So this is an interface, a screenshot of the user interface. You will take a look in more details in our demo later. Now that you have learned more about our deployment process, here I'd like to summarize the key benefits of using LLM solutions integrated into the Leap platform. First, secure deployment. All LLM components are deployed securely using our internal VM resources. As shown in the architecture overview before, this ensures that sensitive client data is protected at every stage. Second, reliability. We've rigorously tested and adjusted the prompts we use for LLM processing to improve quality control. This helps reduce issues like hallucinations and solves problems caused by limited context window, ensuring more coherent responses. Third, enhanced synergy. The outputs generated by the LLM are actionable within the broader platform. For example, summarizations or tag classifications can be linked to other features, creating synergies between different functionalities on the platform. Fourth, high adaptability. Our system is designed to be adaptable. We can fine-tune LLMs to meet specific client needs. We can also support more precise document retrieval or generating more relevant content through a technique called retrieval augmented generation. Fifth, low cost. Currently, the LLM components integrated into our platform will be provided free of charge. There are no additional costs for LLM components, summarization, and text generation that are introduced today, making it a highly cost-effective solution for clients looking to benefit from AI-powered tax applications. Now that we've explored how LLM solutions have been integrated into the Leap platform, you can see how these technologies have the potential to enhance efficiency and adaptability in tax processes. But like any emerging technology, implementing LLM comes with its own set of challenges. So in this section, I'll talk about some of the major problems we encountered during the development of LLM-based solutions and the strategies we adopted to address them. And these problems mainly affected document summarization and keyword extraction. which is a key step in text generation. So the first major issue we faced, especially with document summarization, was the context window limitation. We are currently deploying the Llama 3 model developed by Meta for our AI features. And like most LLMs, Llama 3 has a token limit, which is 8,000 tokens. This means that when we try to process longer documents, the model simply couldn't handle them in a single prompt, leading to incomplete or inaccurate results. And when it comes to keyword extraction, another common challenge arose. The model would often extract irrelevant keywords. This was problematic because instead of pulling out meaningful and focused terms, the LLM would occasionally include words that were too generic or didn't accurately represent the document's main ideas. We also ran into an issue with the LLM not always following instruction precisely, even when we gave clear, specific instructions for extracting certain keywords. The model sometimes produced results that missed the mark, which meant we needed a way to improve its adherence to guidelines. To tackle these challenges, we implemented several solutions: chunking strategy, few-shot prompting, and chain of thoughts, as well as prompt chaining. These terms may sound unfamiliar to you, but I will explain them when I move to some examples of these three problems and explain how we managed to effectively tackle them. So the first major issue we had was dealing with long documents due to the context window limitation in LLMs. As mentioned before, here is how we address this issue using a chunking strategy. This involves splitting long documents into smaller, manageable chunks, summarizing each chunk individually, and then creating a final summary by combining those chunk summaries. This approach allowed us to bypass the token limit and still produce comprehensive summaries. As an example, I used a document from OECD Legal Instruments titled Recommendation of the Council on Artificial Intelligence. The document was much longer than the LLM's 8,000 token limit, so I split it into 4 chunks. Afterwards, so each chunk within the context length limit of the LLM. I let LLM summarize each chunk separately. Afterwards, I combine the summaries of each chunk and ask LLM to summarize that collection of summaries, giving me the final summary of the original long document. An important technique we used here is to maintain logical coherence between chunks. To do this, we overlap about 20% of the tokens between each chunk to ensure that the connection between them remains intact and nothing critical is lost in the transition. So that means in the beginning of each chunk, there are about 20% of the tokens are the same as the end of the previous chunk. Another challenge we encountered during keyword extraction was the irrelevant keywords problem. To solve this, we used a combination of few-shot prompting and chain of thought techniques. So few-shot prompting involves providing the model with a few examples of how we want it to behave, which helps it generate more accurate results. Chain of thought, on the other hand, encourages the model to reason through its answers step by step. These techniques helped guide the model to extract more relevant keywords. Let me further explain this through a real-life example. Often, LLM would extract generic keywords like income, tax, report, terms that were too broad and didn't capture the true meaning of the document, as shown in the conversation I had with ChatGPT-4. So initially, I used a zero-shot prompt to extract keywords from a text document. Zero-shot prompt means when you give the model a task with no examples to guide it, it simply generates a response based on the prompt alone. So this prompt didn't give good results. As you can see, ChatGPT-4 returned generic words like income, taxes, indicators, which didn't capture the essence of the document and didn't give us much information value. And on the right side, I applied the few-shot prompting combined with chain of thought reasoning. In this case, I provide an example of another text and highlighting how the LLM should think through the task by identifying first the main point of the text, and then selecting the most relevant keywords that highlight this main point, as well as excluding keywords that are too generic. As a result, the model extracted much more accurate keywords, as you can show the green highlight here, that these words focused more on the core things of the document. So as you can see, chain of thought prompting helped the LLM reason through its task, leading to better keyword extraction. And another tricky challenge we tackled was the failure of LLM to precisely follow instructions. Even with clear guidelines, LLMs can miss important details or include irrelevant terms. We address this problem using prompt training. Prompt training is a technique where you create a series or chains of prompts and responses, with each prompt building upon the information generated by the previous responses. So this technique lets the LLM review its own outputs and refines its results based on additional prompts, which ensures that it adheres more closely to our criteria. Here is an example. I asked ChatGPT-4 what financial topics are mentioned in this document. So this document discusses topics like credit, investment, and accounting. However, the LLM returned personal taxation along with other relevant terms. Since personal taxation wasn't mentioned in the document, I issued a follow-up prompt asking the model to review its response and correct any mistakes. In the second attempt, it recognized the error and removed personal taxation from the list. So it's clear that prompt training allows the LLMs to refine its outputs by reviewing and improving its initial response, leading to more accurate and relevant keyword extraction. On the right side of the slide is a summary of how we combine chain of thought and prompt training in practice. We start with a simpler prompt to extract relevant tax or finance-related keywords from a document. Then we aggregate keywords across all documents, determine a criteria to eliminate any inappropriate terms. For example, some keywords are too specific, some are just numbers, some are too generic, etc. And apply chain of thought reasoning to exclude these keywords and refine the results. Finally, we use prompt training to evaluate each keyword's relevancy and generate a final, more accurate list of keywords. This method has significantly improved the precision of our keyword extraction process and made our text generation more reliable. Now that I've walked you through the development approach we've taken to address some of the challenges with LLM solutions, let's move on to the live demo. I'll give you a first-hand look at how these LLM features like document summarization and text generation works in real time on our platform. Just a second. So here you can see is our platform deployed on my local PC, and I have already uploaded some documents in advance and has asked the LLM to generate the tags as shown here, and also some summaries generated by the LLM. So the document we use are mostly chosen from OECD documents, and some documents are, for example, are included guidance on transfer pricing documentation and country-by-country reporting, which is available in different languages like English, French, and Chinese. So I upload these documents of different language, but mean the same thing to see if they are consistent. As you can see, for these three documents, the text generated for Chinese and French, they are exactly the same. They talked about BEPS, country-by-country reporting, and transfer pricing documentation. So, and the English one, because the original document is a bit longer than the French and Chinese one, so it had generated a bit more text, but the overall ideas are coherent. Now I'd like to show you how this works in real time. So we'll upload a file in Chinese. I find this file from the Chinese National Bureau of Statistics that talked about that the Chinese economy has a stable growth in August. And why I chose this Chinese document is because I suppose that many of you may not be familiar with this language. So this is to demonstrate that when you have lots of documents with languages you're not familiar with, you can use our platform to help you understand the main point of that document. So here I have transferred this into PDF on my PC, and it's this file. So I will upload it, and I will choose some parameters. Like this is for about China, and it's for the year 2024. And it's for classification. It's not important here. So now you can see this document is uploaded on the platform. And at the same time, however, at the same time, so on the background of my PC, the LLM is processing this data, and it will generate the result in a couple of minutes. So while we wait for the result, I'd like to show you some other feature of the platform. For example, it's the content search function. As we used OCR to convert all documents from files to text, so we can actually search keywords and they will pump up for documents that include those keywords. So you can search in their content or search by file names. For example, if I tap transfer pricing, as we have lots of documents for transfer pricing. So you can see it shows 785 results within all these 8 documents. So let's click one. And you can click on this window, and then it will highlight, you will see in which part of the document the word transfer appeared. So this will be very helpful when you need to search a word and when we want to find in which part of the document you can find this word. So now I think LLM has processed about this document. Let's refresh the page to see if it's updated. So yeah, it's this document. So now we can see that for this document that talks about Chinese economy in August, it generates text like, let's first take a look at what this document is about. So it talks about the Chinese economy in August, and it mentioned some key index like industrial growth, market sales growth, fixed assets, import, export, and consumer price index, and the producer price index. So, and you can see here with the AI generated text, it very well captured some of the main ideas like consumer price index, economic growth, fixed asset investment, industrial production growth, inflation rates, producer price index, retail sales growth, text like that. And also we can take a look at the summary. So it has a pretty decent summary that grasps the main idea of that document. In the first sentence, it says Chinese economy demonstrated a stable growth in August. So this fits and is consistent with the original document. But sometimes if the model generates text that you don't like, we are also having a feedback system. So for example, if you click here, you can see all this text being generated. And next to them, there is a thumb down button. That means you don't like this tag. So you can click on it and you can say why you don't like this tag. Maybe you can say this is not mentioned. Sorry, I'm using a French keyboard. So this is not mentioned. And then you can send feedback. And then we, in our backend, we will catch this feedback. And you can also, at the same time, you can suggest if you find a missing tag that you would like to suggest, you can add one more. For example, you can say exports growth, for example. Then this tag will be, this feedback will be sent to our database as well. And when we have accumulated enough amount of feedbacks, we will use this kind of feedback to fine tune our LLM used dedicated to your company. in order that in the future it will generate more consistent and more customized tags that meet your criteria. And also at the same time, you can provide feedback for the summary here as well. We have a 5-star rating system. For example, if you can clear in the page I showed you before, and you can also rate the summary here. So for example, if you don't like this summary, you can give it a low star, like 2 stars, and you can tell us why you don't like this summary. So it's not correct, for example. And when you send us a feedback of very low rating with a comment, and when we see multiple users have this same problem, same low rating for this document, then we will put it in our batch process. But what is to regenerate a summary? But what is different this time is that we will also include the user's feedback into our prompt so that the LLM can avoid this problem and address the problem to generate a summary that meets your criteria better. So, and basically, this is all that we would like to show on this demo. And one extra function I'd like to see here is that you can download this file. And also, yes, so you can also view the document from this page. And you can as well, you can export them in a Excel format. So now I have downloaded them. I will show you the documents I get. Oh, so this is the result of when we download the Excel file. So you will see all the AI generated summary and some other tags of your documents that you can work with Excel as well. So yeah, that's all for the demo. And let's go back to the slideshow. So as you can see on our demo, our LLM components are designed to make document management both faster and smarter. Users can rely on these summaries to quickly access important information, and the tags ensure the retrieval of relevant documents. So now I'd like to share the next steps in our development. As I've shown you, we are implementing summarization. We have implemented summarization and classification through tag generation on our platform. Next, we will be developing text generation for transfer pricing documentation. Though we focus on using LLM only for specific parts, like some of the factual analysis and industry analysis, while automating others in a more structured and consistent approach. Additionally, data extraction is also being developed to help users interact with their uploaded documents more effectively. So we believe these LLM solutions will add even more value to the platform. I will show you next an example of data extraction, that is to develop an interesting tool that will allow users to interact with their document database in a more conversational way. So this tool uses a technique called retrieval augmented generation. It can answer questions based on specific documents from users' database. So I will show you how RAG works through this example. So if a user asks which company among Google, Apple, and NVIDIA reported the largest profit margins in their third quarter reports for 2023, the query is first converted into a set of numbers through word embeddings. You can think of it like each word receiving an ID card, as we discussed earlier. At the same time, the financial documents stored in the database are split into chunks of similar size, and these chunks are also converted into numbers or sets of ID cards. The system then compares the query to these chunks, finding the closest matches, whether that's one chunk or several chunks, depending on the setting. These matching chunks are then passed to the LLM as additional knowledge into the prompt to help generate a precise response. So the LLM processes this information and produces an accurate answer, like NVIDIA had the largest profit margin. while also citing the original document from which the information was retrieved. This is possible because each chunk of data is clearly labeled and organized when they pass to the LLM. So the key benefit here is that users no longer need to manually search through large volumes of documents. And with this tool, they can ask questions and get both the answer and the source, helping them find the information they need quickly and reliably. We're also working on another important feature, a user feedback system for LLM-generated outputs, as I've shown in the demo. This system will allow users to provide direct feedback on summaries and tags, helping us continuously improve the performance and accuracy of the LLM to better meet their needs. Since the feedback system how it works had been introduced in demo, so I'd like just to add one comment for this slide. You may have seen such feedback systems in other LLMs like ChatGPT, but those systems can have certain limitations. For ChatGPT, with a wide range of users offering different opinions of what a good response should be like, it's unclear whether individual feedback is considered. And OpenAI isn't transparent about how or when the feedback is used to improve their model. At Algonomia, as each client company has its own dedicated LLM, so only feedback from users within that company is taken into account. This makes the LLM more tailored to their specific needs over time. Plus, we maintain open communication with the users, ensuring they know how and when their feedback is applied to improve the system. That brings us to the question and answer session. I'm happy to answer any question you may have about topics we have covered today. Please feel free to type your questions into the chat, and I'll do my best to address as many as possible.